We also have a phi m in here. So phi m is 0.75. And this is just a generic value directly out of the code. Of course, PF is our maximum factored axial load. PC is our critical load. So PC, this is based off of the Euler-Buckling theory. So phi squared EI over KL squared. So again, this is LN is the terminology that we're using right here. And you'll notice that here we run into a little bit of a problem, right? So this PC is only necessary as part of this formula, which we're using to calculate MC. It involves stiffness, right? We have to actually calculate an EI. Now, so far we've been ignoring that calculation. We've been doing our beams and slabs. We had that nice little table that said as long as my thickness exceeds some minimum value, then I don't have to worry about deflection calculations. Now, there may still be times that we might want to do a deflection calculation, and for the most part, they're exactly the same as what we looked at with wood and steel, with the exception of calculating I. Here we now have to come up with the appropriate value for I. And when we're talking about bending, it can get a little bit complex because I need to figure out the actual stress in the beam and determine what stress is necessary to cause cracking, so I can figure out how much of the beam is cracked and come up with an effective I. And there are formulas for that in the book, which we didn't have a chance to go through. But we'll look at calculating this EI here as it relates to our concrete columns. So I want to start by pulling off some of the tables out of the book. Yes? I would have to look that up. LN is clear span. LU.
LU is
unsupported length, yeah. LU would be unsupported length. Versus LN, which is clear, which is, so that's going from bottom of slab to top of slab.
okay.
Yeah. Okay, so the first one we've got here, I've got a few pages that are just scanned directly out of the concrete handbook. And then we also have the additional PDF that is downloadable, so a portion of the concrete design handbook that they have decided not to actually include in the handbook. All right, so the first one here shows various values of K based on different types of support conditions. So it supports at the top and supports at the bottom. And by and large, what we're looking at is this kind of configuration here as your standard configuration, so K is 0.9. You see they vary, they do have a pin-pin situation listed here with a K of 1. And then we go down all the way to the other side, which is as close as you're going to get to a fixed situation, and using a 0.67. And then everything kind of varies in between those values. Right, again, most things are not pure pin-pinned or pure fixed, but they're somewhere in the middle. So somewhere in this range here is kind of what we're typically using. So what we've got here, when they use the term elastic, right, they're using the term here, elastic, and here, is that the section properties or stiffness between the beam and the column are approximately equal. When you're talking stiff, what that means is that the section properties of the beam are considerably bigger than that of the column. Right, so effectively what that means is that the slab, even though you're putting some load on it, does not actually rotate. Right, so all the rotation is due to the column itself. Right, and you can also think of the hinge as being a complete opposite, where the slab is considered, or the beam is considerably weaker than the column. But like I say, for the most part, we tend to be working kind of within that middle quadrant. Right, so there's some slight differences as to whether or not this is the top floor or a middle floor. And the same thing here, bottom floor versus a middle floor here. But again, they're just approximate values that are somewhere in between a pin and a fixed scenario. You'll notice as well with this 0.67, remember the theoretical value for fixed is actually 0.5. Right, so again, what we've got here is a recommended value. Unlike the steel code, which lists both, this just lists the one, which I actually think is a better approach. So if you have a table with theoretical and recommended, it's quite likely that somebody is going to pull something off of the wrong column and get the wrong number as a result of that. Yeah, so a lot of information. So this part here, we actually haven't talked about this. This is actually the commentary to the code. In the previous versions of the handbook, this actually used to be part of the handbook and not part of the code itself. But for some reason, they decided to take this exact same picture that used to be part of the handbook and incorporated it directly into the commentary for the code. Right? So the commentary all starts with the letter N. Right? So this is relating to section 10.15.3. Right? So you see section 10.15.3. This is the section in the code where all of these formulas are found. So the N now are the notes associated with that section. Right? So you can get more detail by reading the notes section. So it's towards the end of the brown pages where all the notes are. And there are notes for just about every clause within there. Okay, now we're getting into the handbook part. So the handbook part, we've got these columns here, which are based on axial load only. So what that means is we're not considering any bending. Right? Now remember that typically we have a certain amount of bending that we're going to be putting on here anyway. Right? You're typically not going to be designing a column for just axial load. That would be kind of rare for concrete. So what we've got here, there are several pages, several copies of these tables. This is a 35 MPa concrete, 400 MPa rebar. Right, there's also a 35 MPa concrete and a 500 MPa reinforcing steel. Not quite as common. This is our standard configuration right in here. And as you look at this, what we're going to see is that, first of all, on one side we have our axial load. It is expressed in terms of meganewtons. And then we have a reinforcing ratio along the bottom. Right, so for the most part, what we do is, just considering axial load only, is I'm going to read up here, and I'm going to find some particular value. Say I've got 5 meganewtons on my column. Loads here for columns can end up being quite a bit higher because they're cumulative as you work your way down the building. So it's not uncommon to see meganewtons being used for the column calculations. And I'm just going to read across here, and every curve that it intercepts is a possible column size that will work based on this axial load. Right, so I'll read across here, and first of all, we see a 650 by 650 just touches it. But technically, these lines actually extend right down. So any larger size is technically okay as well. So I'm going to see that 650 by 650 with a relatively small reinforcing ratio, about 0.5%. As I move across here, next one is a 600 by 600, then a 550 by 550, and a 500 by 500. And then as we get out here, there's a 450 by 450, and this one has the highest reinforcing ratio. This row, just like the AS over BD that we were talking about before for beam design, is basically the same idea. It's a reinforcing ratio. Row here. It's a reinforcing ratio, so it's an area of steel divided by area of the column. You'll also notice that within this table, they list the gross area. Right, so a 550 by 550, of course, is just 550 millimeters times 550 millimeters, but they've already given it to us in meters squared. You'll see as we go into the calculations, one of the calculations that we use, it actually makes sense to put things in meters rather than millimeters. Right, so that's our first table that we're going to look at.
Peter?
So, yes?
This PR max, that's the same as our PF?
Yeah, so for the most part, we're going to set PR equal to PF. That's right, so take our design load, read across here, and come up with various different column configurations that can work. Now, if I go and say I've got 5 meganewtons, and I read off here, and I say, okay, let's try a 450 by 450. That means just based on axial load only, I need a fairly high reinforcing ratio. Right? That does not leave any room for moment calculation. Right, so I wouldn't typically go way out here to the end. I'm going to go somewhere in the middle here so that I can now deal with the moment component as well. So we will likely end up putting a higher reinforcing ratio than what's listed down here once we take that into account. Now, this is our table, and there's a couple of pages here. So one with reinforcing on all 4 sides, and then one with reinforcing on 2 sides. And this just enables us to figure out for a particular column size and a particular reinforcing ratio, or reinforcing pattern, what that ratio is. Right, so these are our reinforcing ratios, so these are those row values in here. So if I'm looking at a 300 by 300 column, right, so this is a square column here, and this would be a rectangular column, right, rectangular out here. So square, 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 right, so if I'm looking at a 300 by 300 column, right, if I put in 8 15 in bars, there's our reinforcing ratio. Right, 12 20 in bars, there's our reinforcing ratio. Obviously with a small column size, I'm not going to be able to put in 20, 30 in bars. So you just can't physically fit them in there. So that's why there's parts of the tables that are left blank. There is also this little line that you see coming across here. And for the most part, we don't need to worry about that line too much. What that represents is if you are above the line, so reinforcing ratio higher, right, so on this side of the line, then what that means is that we have some special considerations in terms of where I put splices in my reinforcing scale. Right, so we're not going to necessarily, if I got a 10-story building with a 10-story high column, have a single piece of rebar that runs a full 10 stories. So I have to put splices in various locations. And there are different types of splices. I can actually physically weld the ends of the bar together. We can put in a screwed connector where I just screw the two ends together. We have a mechanical connector where they overlap, and then there's two plates with a bolt system that clamp them together. And so there are a variety of different systems in here. So if I'm above the line here, it just means we have some special considerations in terms of how and where I splice them. Right? So in terms of our design, we don't really need to worry about that too much at this point. So this table here, reinforcing on all 4 faces. So that means when we take a look at our pattern of reinforcing, so with a square column in here, right, so 8 bars. So that means 1 in each corner, plus an additional 1 on each side. Right, there's your 8 bars. Right, if I go with 12 bars, I'll be putting that kind of configuration. Right, and then 16 bars, it would be 5 per side, and 20 and so on, get a pattern. Right, so it's just referring to the number of bars per side. Notice we don't put stuff in the middle. That's not really going to be necessary because as you start bending this, anything that's in the middle is close to the neutral axis and doesn't actually take any significant load. Right, so it's just around the outside edges. Now this is reinforcing on 4 faces. We can also get reinforcing on 2 faces. Right, so 4, 6, 8, 10. So again, this would be 2 bars on either side, 3 bars on 2 sides, 4 bars on 2, 5, and 6, and so on. Right, so similar kind of configuration in here. Right, so here's kind of showing the pattern. So bars on 2 end faces, and then bars on all 4 faces. Right, and then they also show some circular ones and some configurations here which are for rectangular columns as well. And we're going to focus on these kind of patterns here to start off with. Again, we're focusing now on taking a look at the moment of inertia calculations, or the EI part. So the first formula we're going to look at is the EI term. It is 0.4 times EC times IG, so E of concrete divided by gross area, and then divided by 1 plus beta D. And I'll talk about that in just a second. Right, so this is not considering any reinforcing, so this is just the stiffness due to the concrete by itself. Now our beta D term is a factor to take into account sustained loads. So beta D is our PDF divided by PF. This is somewhat similar to the rationale behind the KD factor in wood design. Remember, that was the load duration factor, and If we had long-term load duration factor, we had a different value than if it was a short-term load duration factor. Right? And so here we're taking into account, this is our axial dead load, but factored, so 1.25 times our dead load. Right? And then our 1.25 dead plus 1.5 live is our factored total axial load. Right? So we just come up with this factor and we divide through by 1 plus beta D in this formula.
So that's just the dead load on the top there, and it's the total load on the bottom.
Yeah, but they are factored.
Factored, yeah.
Yep. Okay, so now we're going to start considering our pattern for reinforcing.
And you said IG is just the gross area?
Gross area, that's right.
How come you changed it from AG to IG? You don't have IG?
Oh, so, yeah, so this is, so gross, this is gross moment of inertia, not gross area. So this is 112 bhq. Right, so that's all that is, at least for a rectangular sector. So when we add in our reinforcing, we're now taking into account not only what the concrete is doing, but now there's a steel term in here as well. So E of steel and I of steel. And our I of steel is a pattern which changes, or at least it's a number that changes depending upon the pattern of the reinforcing. Right, so as we look at different reinforcing patterns, we will end up calculating a different IST. Our IST, we're going to be basically considering plus AD squared. Right, when we take a look at, say, moment of inertia about this axis right here, what we've got is a moment of inertia of a bar plus an AD squared term, right? And then I'd have to multiply by 8 in this particular configuration. Right? So moment of inertia plus AD squared. Right? So we look at the AD squared term, and we need to come up with that D, and we see that we relate the location of the bar using this term gamma. So we now have our overall H and B. Again, we're going to focus on square columns here, but where H and B are the same. But basically what we've got is we've got a cover distance, and then we've got a skirt running around there as well, as shown on that cross section. And then we're going to have the location of the bar. So rather than calculate that D value that we were looking at, which went from one side to the center of the reinforcing, now we've got this gamma term, which goes from the center of reinforcing to center of reinforcing. Question?
For factor with non-reinforcing,
Yes.
what would that be for? Like footings or when would you not have reinforcing?
You know, in practice, I don't think I've ever used that.
Yeah.
We don't use unreinforced concrete. I suppose technically, if you had a pre-stressed condition where I take the entire concrete section and squish it together, so there are no tension forces being developed, then I don't have to put in tension reinforcement.
Would you put reinforcing in footings? Like,
Yes, we'll still put reinforcing in the footing,
Okay.
because the footing is going to bend right in two directions.
okay.
So yeah, and like I say, in practice, I don't think I've ever used that, but it's kind of the starting point that we're looking at just due to the effect of the concrete alone, and now we're going to add in the effect of the steel. Right? And as we plug in the IST, we're going to plug in some different values. Now, E is concrete. This is our 4,500 square root of F prime C, the same value that we were using before. IG, again, 112 DHQ. We talked about a 1 plus beta D. ES is just going to be 200,000. So it all comes down to this IST value. So a different reinforcing pattern is going to give different values of IST. So I think this is probably a good spot to break for now. And then after the break, we'll take a look at how those different reinforcing patterns can affect this number.